Objects in motion stay in motion. Newton's first law. This foundational principle, also known as the law of inertia, is deceptively simple yet revolutionary. Before Newton, Aristotle's views dominated, claiming objects naturally came to rest unless a force kept them moving. Newton shattered this view by proposing that motion doesn't need a cause to continue. Stopping does. An object at rest remains at rest, and one in motion stays in motion with constant velocity unless acted on by a net external force. This explained not just the fall of apples, but the orbit of planets and the stability of galaxies. It underpins our understanding of collisions, vehicle dynamics, sports physics, and even interplanetary travel. When a spacecraft shuts off its engines, it doesn't stop. It coasts indefinitely unless acted upon. This principle is the gateway to classical mechanics, and it's often one of the first major aha moments for students of physics. It fundamentally shifts our view from needing to explain motion to needing to explain changes in motion. It also implies a universe governed by consistent rules, a concept that fuels all of modern science. Gravity pulls everything toward everything else. Gravity is one of the most pervasive forces in the universe. Newton's insight that every mass attracts every other mass with a force that decreases with the square of the distance was a breakthrough that united the motion of falling objects and planetary orbits under the same law. This concept introduced a universal order to what once seemed like separate phenomena: the tides, the orbits of moons, and even the structure of the universe itself. It allows us to predict the motion of satellites, build stable structures, and understand phenomena like black holes and neutron stars. It also lays the foundation for Einstein's general relativity, where gravity becomes the curvature of spacetime itself. In daily life, gravity affects everything from how we walk to how we build. It's why we need energy to lift things, why rivers flow downhill, and why time itself ticks slower on Earth's surface than it does at high altitudes. The elegance of this invisible force binding the cosmos continues to inspire awe centuries after its discovery. Force equals mass times acceleration. This elegant equation, Newton's second law, is the engine of classical mechanics. It tells us that the amount of acceleration an object experiences is directly proportional to the force applied and inversely proportional to its mass. This means that heavier objects require more force to accelerate the same amount. It's used to design vehicles, analyze athletic performance, and understand planetary motion. In engineering, it helps calculate stresses in buildings, bridges, and aircraft. It's also critical in understanding safety systems, like seatbelts and airbags, which rely on managing force and acceleration during a collision. More abstractly, it ties together motion and the causes of motion, bridging the gap between the math of kinematics and the reality of physical interactions. It turns the study of motion into a predictive science, enabling everything from rocket trajectories to biomechanics to earthquake modeling. Without this law, physics would be a collection of disconnected observations rather than a coherent framework. It allows us to understand not just how things move, but why they move in the way they do, which makes it one of the most fundamental principles in all of physics. For every action, there's an equal and opposite reaction. Newton's third law describes the symmetry of interactions. Forces always come in pairs. If you push against a wall, it pushes back with equal force. This might seem trivial, but it's the foundation of propulsion, structural support, and even our ability to walk. Every step you take involves pushing against the ground, which pushes you forward in return. This law is essential in designing engines, aircraft, rockets, and even robots. In collisions, it explains why momentum is exchanged between objects. In sports, it governs how we throw, kick, and jump. On a cosmic scale, it's how solar winds shape planetary magnetospheres and why galaxies can recoil after collisions. Philosophically, it reveals a universe built on balance and reciprocity, where no force acts in isolation. It ensures that physical systems conserve momentum and that energy flows are accountable. Even in quantum mechanics and field theory, the concept of equal and opposite responses appears in more abstract forms. This law teaches us that interactions are never one-sided. They are mutual exchanges of influence that ripple out across time and space. Energy is the ability to do work. Energy isn't just something we use to charge our phones or fuel our cars. It's the fundamental capacity for change. Whether it's mechanical, thermal, chemical, or nuclear, energy is the underlying currency of the universe. The concept of work, a force applied over a distance, makes energy quantifiable and universally applicable. The conservation of energy tells us that energy can't be created or destroyed, only transformed. This principle powers engines, drives ecosystems, and dictates how the universe evolves. Solar panels convert radiant energy into electricity. Muscles convert chemical energy into mechanical motion. Stars convert nuclear energy into light and heat. The universality of energy allows us to connect biology with physics, chemistry with astronomy, and geology with engineering. Every scientific discipline depends on energy as a unifying idea. It defines efficiency, underlies thermodynamics, and even helps explain why time appears to move forward. Understanding energy gives us insight into sustainability, technology, and even the future of civilization itself. It's not an abstract concept. It's the fuel behind everything from the smallest microbe to the largest galaxy. Velocity is speed with direction. Velocity adds direction to the concept of speed, making it a vector. This distinction is crucial. You can be moving at a constant speed, but still be accelerating if your direction is changing. That's why cars on a circular track have changing velocities, even if their speedometers are constant. Velocity is what makes motion predictable. It allows us to define displacement, how far you've gone from where you started, momentum, mass times velocity, and relative motion, how two moving things see each other. Velocity plays a central role in navigation, sports, and mechanics. Air traffic control relies on velocity vectors to keep planes safe. GPS systems compute routes based on velocity. In Einstein's relativity, an object's velocity affects how time flows and how lengths appear. In everyday life, understanding velocity helps us interpret everything from a fast pitch in baseball to the behavior of storm systems. It's also essential in space exploration, where tiny changes in velocity can determine whether a spacecraft reaches its destination or misses by millions of kilometers. Acceleration is a change in velocity over time. Acceleration is not just increasing speed, it's any change in velocity, including slowing down or changing direction. It's what you feel when an elevator starts moving, a car brakes suddenly, or a roller coaster crests a hill. Understanding acceleration helps us design safer vehicles, more efficient engines, and better athletic training. It's also central to understanding gravity, orbits, and the behavior of celestial bodies. In physics, acceleration connects force by Newton's second law and energy as it involves work. It's why astronauts experience g-forces during launch and re-entry. It's why sprinters train for explosive starts, and why satellites must constantly adjust to maintain orbit. Acceleration plays a huge role in structural design, whether building roller coasters, race cars, or skyscrapers that sway with the wind. Even in psychology and human factors engineering, we study how acceleration affects the human body and perception. The concept is simple, but the applications are vast and powerful. Friction slows things down. Friction is the resistive force that opposes motion between two surfaces. It's why you don't slide forever after pushing off. It's also why tires grip roads, why sandpaper works, and why machines wear out. Friction converts kinetic energy into heat, which is why brakes get hot and hands warm up when rubbed together. It plays a role in geology, earthquakes, biology, how we walk, and engineering, lubricants, bearings, and engines. But it's not always a nuisance. Friction allows us to grip tools, climb hills, and write with pencils. Managing friction is a central problem in engineering. How to reduce it in machines, but maximize it where grip and traction are needed. Friction is one of the most tangible forces we interact with daily, yet its microscopic origins in molecular interactions are still a rich field of study. Understanding how friction works has led to breakthroughs in everything from nanotechnology to earthquake prediction. It's a reminder that even a wasteful force can be harnessed for control, safety, and stability. Mass is not the same as weight. Mass measures how much matter an object contains. Weight is the force of gravity on that mass. This difference becomes obvious in space, where astronauts are weightless but still have mass. Mass is intrinsic, while weight depends on the gravitational field you're in. This distinction is crucial in physics and engineering. It affects everything from how we design spacecraft to how we measure matter in chemistry. On Earth, we often conflate the two because gravity is constant, but in space or on other planets, the difference becomes vital. Mass also defines inertia, an object's resistance to changes in motion. It helps determine kinetic energy, momentum, and gravitational attraction. Weight, on the other hand, changes with location. A person on the moon weighs less than on Earth, but has the same mass. Understanding this difference is essential when dealing with systems that involve varying gravitational fields, such as satellite deployment, lunar landers, and deep space probes. It's a fundamental idea that clarifies many misconceptions and forms the backbone of accurate scientific reasoning. Free fall is acceleration due to gravity alone. In free fall, the only force acting on an object is gravity. Air resistance is gone, and the object accelerates uniformly at about 9.8 meters per second squared on Earth. This condition allows us to study motion in its purest form. Galileo's early experiments with inclined planes and dropped objects revealed that all masses fall at the same rate in a vacuum, contrary to earlier beliefs. Today, we use the concept of free fall in understanding orbits, designing drop towers for physics experiments, and simulating microgravity. Astronauts in orbit are in constant free fall around Earth, which creates the sensation of weightlessness. This concept is also critical in calculating projectile motion, understanding escape velocity, and modeling gravitational slingshots. In education, it introduces students to acceleration, kinematics, and Newton's laws. Philosophically, it helped humanity transition from the idea of Earth as a static center to understanding motion as relative and governed by universal laws. Free fall is more than just falling. It's a doorway into the deeper mechanics of the universe. Light behaves like a wave. For centuries, scientists argued about the true nature of light. Was it made of particles or waves? In the 1800s, experiments like Thomas Young's double-slit experiment provided stunning evidence that light behaves like a wave. When light is passed through two slits, it creates an interference pattern, bright and dark bands, just like ripples overlapping in water. This demonstrated that light doesn't travel in straight lines like bullets, but spreads, bends, and interferes like sound or ripples on a pond. This wave model explained many everyday phenomena like reflections, refractions, and rainbows. It laid the groundwork for understanding color as different wavelengths of light, and it helped shape technologies like lenses, fiber optics, and lasers. But what's most fascinating is that this wasn't the end of the story. Later discoveries showed that light also behaves like particles in certain conditions, revealing that nature is even stranger than we thought. Still, the wave model of light remains one of the most elegant ways to describe the flow of energy through the universe. It reminds us that things we once saw as fixed, like light traveling in a straight path, are often more flexible, more mysterious, and more interconnected than they appear. Sound travels in compressional waves. Sound isn't just something we hear, it's a vibration, a physical movement of energy through a medium. When something makes a sound, like your vocal cords or a speaker cone, it pushes on the air molecules next to it, compressing them together. These compressed molecules then bump into their neighbors, transferring the vibration outward in all directions like a chain reaction. This pattern of compressions and rarefactions, areas where air molecules are squished together or spread apart, is what we call a sound wave. Unlike light, sound can't travel through a vacuum. It needs matter to move through: air, water, even steel. That's why astronauts can't talk to each other in space without radios. The speed of sound also changes depending on the medium. It's faster in solids, slower in gases. This principle explains everything from why thunder follows lightning to how submarines use sonar to map the ocean floor. Understanding sound as a wave opens the door to acoustics, music theory, and audio technology. It's also central to how we understand speech, hearing, and even medical imaging like ultrasounds. Sound waves are invisible, but they're everywhere, shaping communication, environment, and emotion. Electricity and magnetism are connected. Once seen as separate forces, electricity and magnetism turned out to be two sides of the same coin. This discovery revolutionized science and birthed modern technology. In the 1800s, scientists like Michael Faraday and James Clerk Maxwell discovered that a moving electric charge creates a magnetic field, and likewise, a changing magnetic field induces electric current. This deep connection became known as electromagnetism. It's what powers electric motors, generators, transformers, and wireless communication. It's how your phone charges wirelessly, how MRI machines work, and how energy travels through power lines. But this isn't just practical, it's profound. Electromagnetism is one of the four fundamental forces of nature. It governs how atoms bond, how light travels, and how electrons orbit nuclei. When you flip a light switch or get a static shock, you're interacting with this elegant force. Maxwell's equations mathematically unified electricity and magnetism into one beautiful framework, a language that describes how electric and magnetic fields move through space and influence one another. This unity was one of the first signs that the universe's forces might not be separate after all, but deeply interwoven in ways we're still trying to understand. Maxwell's equations unify electromagnetism. James Clerk. Maxwell's four equations did something monumental. They unified electricity, magnetism, and light into a single, coherent framework. These equations describe how electric fields are created by charges, how magnetic fields arise from moving charges, and how these fields propagate through space. Most astonishingly, they predicted that electromagnetic waves, light, travel at a constant speed through a vacuum. That meant light itself is an electromagnetic wave rippling through the invisible fabric of space. This discovery laid the groundwork for Einstein's theory of relativity and modern physics as a whole. Maxwell's equations also underpin every piece of technology that involves electricity or light. radios, microwaves, computers, cell phones, and satellites. They describe how antennas transmit and receive signals, how light bounces and bends, and how energy can move through space without a physical medium. More than just equations, they're a bridge between the physical and the mathematical, a set of rules that help decode the behavior of the invisible world. Maxwell showed that the world isn't made of isolated forces, but of deep connections. His work marked the beginning of the modern age of physics. Heat is energy in motion. Thermodynamics begins. Heat isn't just hotness, it's energy on the move. It's the motion of molecules jostling, bumping, and vibrating. When you touch a warm mug, energy flows from the faster moving particles in the mug to the slower moving ones in your skin. This transfer is what we perceive as heat. The study of how heat moves and behaves is called thermodynamics, and it's one of the most important foundations in physics. It governs engines, refrigerators, weather systems, and even the behavior of stars. Thermodynamics taught us that energy can change forms, chemical to thermal, kinetic to potential, but it doesn't disappear. It also taught us that this transformation has limits. Not all energy can be used perfectly. Some of it always becomes unusable, increasing disorder in the system. This is entropy, and it shapes everything from melting ice to the aging of the universe. Understanding heat as moving energy connects the microscopic world of atoms with the macroscopic world of machines. It also reveals a surprising truth. The universe tends toward disorder, and every act of doing work or generating heat plays into that balance. Thermodynamics doesn't just describe heat, it tells us about the arrow of time itself. The first law, energy can't be created or destroyed. The first law of thermodynamics is one of the most fundamental principles in all of physics. It tells us that energy cannot be created or destroyed. It can only be transferred or transformed. This principle is also known as the law of conservation of energy. Whether you're burning gasoline in a car, charging your phone, or digesting food, energy is simply changing forms, from chemical to kinetic, from electrical to thermal. The total amount of energy in a closed system always remains constant. This might sound abstract, but it governs everything around you. When a roller coaster races down a track, gravitational potential energy is converted into kinetic energy. When you eat, your body transforms chemical energy into motion and heat. Even the sun, burning for billions of years, isn't creating energy from nowhere. It's converting mass into energy via nuclear fusion. The first law gave scientists a way to account for all the energy in any system, from engines to ecosystems. It also served as a powerful check against impossible machines, like perpetual motion devices, because such devices would have to create energy from nothing. It's a law that makes our universe predictable, logical, and quantifiable. The second law, entropy always increases. The second law of thermodynamics is profound, unsettling, and strangely beautiful. It states that in any closed system, entropy, the measure of disorder, will always increase over time. What does that mean? It means that energy becomes less useful as it spreads out. Heat flows from hot to cold, not the other way around. Your coffee cools down, ice melts, structures decay. This law introduces irreversibility into the universe. It explains why time seems to move forward, not backward, because disorder increases, not decreases. In a perfectly ordered system, like a brand new computer or a freshly made snowflake, the molecules are in specific low entropy configurations. But over time, randomness creeps in. The system loses its precision and increases its entropy. No matter how carefully you arrange things, entropy always wins. It governs everything from the efficiency of engines to the eventual fate of the universe. The second law suggests that in the very long term, all energy will eventually spread out so evenly that no work can be done, a state known as heat death. This principle shapes our understanding of time, life, and decay, reminding us that while order is precious, disorder is inevitable. Temperature is the average kinetic energy of particles. We often think of temperature as just how hot or cold something is, but physics gives us a more precise and more revealing definition. Temperature is the average kinetic energy of the particles in a substance. That means when you heat something up, you're not just making it feel warm, you're literally making its atoms and molecules move faster. In a hot gas, for example, particles zip around with high speed and energy. In a cold one, they move slowly. This understanding connects the invisible world of atoms with the tangible sensations we feel every day. It's what makes thermometers work. It explains why metal feels colder than wood. Even at the same temperature, it conducts heat away from your hand faster. It also lets us understand pressure in gases, phase changes like melting and boiling, and why you can cool something by evaporating liquid off of it. This concept is essential in everything from climate science to engine design to chemistry labs. Temperature isn't just a number, it's a window into the microscopic dance of matter, and it reveals how deeply connected motion, energy, and heat really are. Pressure in gases comes from particle collisions. What is pressure really? When you inflate a balloon or feel your ears pop on an airplane, you're experiencing the collective force of countless tiny particles colliding with surfaces. Pressure in gases is the result of gas molecules moving rapidly in all directions and constantly bouncing off the walls of their container. Each collision exerts a tiny force, and when you add up trillions of these per second, the result is what we feel as pressure. This concept transformed our understanding of fluids and gases. It led to equations like the ideal gas law, which relates pressure to temperature, volume, and the number of particles. It explains why tires inflate, how lungs expand and contract, and why scuba divers need to ascend slowly to avoid decompression sickness. It's also the foundation of barometers, vacuum systems, and even weather prediction. On a deeper level, gas pressure reminds us that even empty air is full of motion and interaction at a microscopic scale. It takes the invisible, chaotic world of atoms and makes it felt in something as ordinary as a soda can or as massive as a hurricane. The conservation of momentum. Momentum is the quantity of motion an object has. It's the product of mass and velocity. But conservation of momentum is what gives it lasting power in physics. It says that in a closed system, momentum remains constant unless acted upon by an external force. This principle explains everything from pool shots to car crashes, from rocket launches to planetary orbits. When two ice skaters push off each other, they move in opposite directions, not by magic, but because their total momentum before and after the push stays the same. In collisions, momentum may shift between objects, but the total momentum of the system remains unchanged. This law lets physicists analyze situations where forces are complex or hidden by focusing on the before and after states of a system. It applies to particles smashing together in accelerators, to asteroids slinging past planets, and to how recoil works when you fire a gun. Momentum conservation is also a bridge to understanding angular momentum and energy. It reflects the symmetry and predictability of the universe, showing that movement isn't random. It obeys deep, elegant rules. The conservation of angular momentum. Angular momentum is like linear momentum's rotational cousin. It describes the motion of objects that spin or orbit. And just like regular momentum, it's conserved. That means in the absence of external torque, the total angular momentum of a system remains constant. This law governs everything from the spin of a figure skater to the rotation of galaxies. It's why a spinning skater speeds up when pulling their arms in. By reducing their radius, they must spin faster to conserve angular momentum. It's also why Earth's rotation slows very slightly over millennia due to the moon's tidal influence. In space, conservation of angular momentum is crucial. Planets spin because clouds of gas that formed them had a tiny bit of rotation. As gravity pulled the gas inward, that spin increased. It's the same principle behind neutron stars, spinning hundreds of times per second after a supernova collapse. Engineers rely on this principle in gyroscopes, satellites, and even drones. Philosophically, it's a reminder that nothing in motion, whether moving straight or spinning, changes without reason. Angular momentum conservation is one of the most universal, elegant, and powerful ideas in physics. It binds together motion, stability, and symmetry on every scale. Work equals force times distance. The idea of work in physics is different from everyday use. Here, work refers specifically to a force causing displacement. If you apply a force to an object and it moves in the direction of that force, you've done work. The formula, work equals force times distance, might seem simple, but it allows us to measure and quantify the energy transferred in all kinds of systems. If you push a box across the floor, lift a weight, or stretch a spring, you're doing work. But if you push against a wall and it doesn't move, no work is done, no matter how tired you feel. This distinction is essential to understanding how machines operate, how energy is used, and how efficient a system is. In engineering, work is central to everything from engines to elevators to cranes. In biology, it explains how muscles convert chemical energy into mechanical action. Work links force and energy. It's how one becomes the other. It's also foundational in understanding power, which measures how quickly work is done. The work formula is a quiet giant of physics, unassuming but immensely powerful, describing the energy behind motion and transformation. Power equals work divided by time. If work tells us how much energy is transferred, power tells us how fast that energy is used. It's the rate of doing work, measured in watts. If two people lift identical boxes to the same height, they do the same amount of work, but the one who does it faster is using more power. This idea helps us distinguish not just effort, but performance. In engineering and physics, power ratings tell us how much energy a machine can deliver per second, whether it's an engine, a light bulb, or a nuclear reactor. The faster energy is transferred, the more power is involved. This principle applies to everything from athletes' output to electricity usage to battery life. A 100-watt light bulb uses more energy per second than a 60-watt bulb, which is why it's brighter and heats up more. Power also bridges physics with economics and infrastructure. It's central to how we generate, distribute, and consume energy. Understanding power lets us measure efficiency, compare systems, and optimize everything from smartphones to skyscrapers. In a world built on motion and electricity, power is the pulse of productivity, the measure of how much energy a system can unleash in a given moment. Buoyancy keeps things afloat. Archimedes' principle. Why do ships float even when made of heavy steel? Why do some objects sink while others bob effortlessly on the surface? The answer lies in buoyancy, described by Archimedes over 2,000 years ago. He discovered that when an object is submerged in a fluid, it experiences an upward force equal to the weight of the fluid it displaces. If this upward force, buoyancy, is greater than the object's weight, it floats. If not, it sinks. This principle governs everything from submarines to hot air balloons to the behavior of icebergs. It explains how fish control their depth using swim bladders and how blimps hover in the sky. In engineering, it's used in designing ships, oil rigs, and even measuring devices. Buoyancy is not only practical, but elegant. It turns weight and volume into a delicate balance of forces. Archimedes' insight was revolutionary. It shifted understanding from the surface, why things appear to float, to the forces underneath. Buoyancy is still a central principle in fluid dynamics, naval architecture, and aerostatics. It reveals how pressure, displacement, and density come together to support weight, and it starts with something as simple as watching an apple bob in water. Centripetal force keeps objects moving in circles. If you've ever been on a merry-go-round or taken a sharp turn in a car, you've felt the invisible pull that seems to push you outward. But what's actually happening is the opposite. You're being pulled inward by a force called centripetal force. It's the inward force required to keep an object moving in a circular path. Without it, the object would move off in a straight line. This force isn't a new kind of interaction. It's just a regular force, like tension, gravity, or friction, acting toward the center of the circle. When you swing a ball on a string, your hand supplies the centripetal force. When Earth orbits the Sun, gravity is the centripetal force. Understanding this principle is crucial to everything from roller coaster design to the motion of satellites. It explains the arcs of planets, the spin of washing machines, and the stability of car tires on curved roads. Centripetal force shows us that curved motion is actually a constant fight against inertia, pulling something inward when it naturally wants to move straight. It's a reminder that even seemingly simple motion often hides deep, elegant forces beneath the surface. Inertia is resistance to change in motion. Inertia is one of the most fundamental, yet deeply misunderstood ideas in physics. It's the reason you lurch forward in a car when it suddenly stops, or why a ball rolling across the floor doesn't change direction on its own. Inertia is the natural resistance of an object to any change in its state of motion. If it's at rest, it wants to stay at rest. If it's moving, it wants to keep moving in the same direction at the same speed, unless an outside force acts on it. This concept is built into Newton's first law, but it goes beyond a formula. It reveals that motion is not caused by a push, but altered by one. Inertia also explains why massive objects are harder to stop or start. They resist change more. That's why a full shopping cart takes more effort to move than an empty one. In the cosmic sense, inertia helps govern orbits and explains why objects in space keep drifting indefinitely. It plays a role in designing vehicles, amusement rides, and even safety gear like seatbelts and helmets. Inertia is not just about laziness in motion, it's about the deep structure of how mass and space interact. Simple harmonic motion explains swings and springs. Simple harmonic motion, SHM, is the elegant pattern behind oscillating systems, things that move back and forth around an equilibrium point. It's what makes a pendulum swing, a spring bounce, or a tuning fork vibrate. The motion is simple because it follows a repeating sinusoidal pattern that can be described with basic trigonometry, and it's harmonic because it's the foundation of wave behavior, music, and resonance. In simple harmonic motion, the restoring force, pulling an object back toward equilibrium, is directly proportional to its displacement. Hooke's law for springs is a classic example. Understanding SHM lets us predict how long a pendulum takes to swing, how shock absorbers dampen motion, and how buildings sway during earthquakes. It also explains how atoms in solids vibrate, how sound waves propagate, and even how electrical circuits oscillate. SHM serves as a bridge between classical mechanics and wave physics. It reveals how nature favors balance, rhythm, and periodicity. Once you understand SHM, you start seeing it everywhere, in clocks, instruments, engineering designs, and even quantum systems. It shows that motion isn't always chaotic. Sometimes it's beautifully predictable. Resonance causes dramatic oscillations. Resonance is one of the most powerful and sometimes dangerous phenomena in physics. It occurs when a system is forced to oscillate at its natural frequency, and the result can be a massive increase in amplitude, often with dramatic effects. Think of a child pumping their legs on a swing. When the timing of their pushes matches the swing's natural rhythm, they go higher and higher. That's resonance. It's the reason why a wine glass can shatter from a singer's voice, or why bridges have collapsed from rhythmic marching or wind. In the right conditions, even a small input of energy can lead to huge responses. Resonance is everywhere, from the tuning of musical instruments to the design of skyscrapers and aircraft. Engineers must design to avoid destructive resonance, especially in structures exposed to wind or vibration. But resonance is also useful. It powers radio receivers, microwave ovens, and medical devices like MRI machines. It even plays a role in the stability of planetary orbits. At its core, resonance shows us that systems have preferred patterns, natural frequencies that, when matched, unlock a deeper energy. It's a reminder that timing isn't just important, it's transformative. Classical mechanics breaks at very small scales. For centuries, Newtonian mechanics explained nearly everything: how planets orbit, how apples fall, how machines operate. But as scientists probed the world of atoms and subatomic particles, they found that classical mechanics simply stopped working. Electrons didn't orbit nuclei like planets. Light didn't behave like just a wave. Events didn't unfold predictably. At the atomic level, particles didn't have definite positions or velocities, just probabilities. This breakdown of classical mechanics gave rise to quantum physics, a completely different set of rules governing the microworld. The realization that the old laws fail at small scales was more than a technical update. It was a philosophical shock. It showed that our intuitive understanding of cause and effect, motion, and determinism doesn't apply everywhere. This shift required a total rethink of what reality is. It led to the discovery of wave-particle duality, uncertainty, and the probabilistic nature of measurement. Still, classical mechanics remains incredibly useful for the macroscopic world. It's accurate enough to land spacecraft, build bridges, and simulate weather. But its limits remind us that the universe is layered, and each layer plays by its own set of rules. Sometimes reality is stranger than we can imagine. Classical physics can't explain blackbody radiation. Blackbody radiation was one of the first cracks in the foundation of classical physics. A blackbody is an idealized object that absorbs all radiation and re-emits energy based solely on its temperature. According to classical theory, the energy it emitted should increase infinitely at shorter wavelengths, a result known as the ultraviolet catastrophe. But in reality, that didn't happen. The intensity peaked and then dropped off. No classical model could explain this. The puzzle was solved by Max Planck, who proposed that energy isn't continuous, but comes in discrete packets, quanta. This idea led to Planck's constant and the birth of quantum theory. It was revolutionary. The idea that energy is quantized changed everything. This small correction explained the spectrum of blackbody radiation perfectly and paved the way for Einstein's photoelectric effect and the development of quantum mechanics. The failure of classical physics to explain blackbody radiation marked a turning point. where physicists had to confront that their understanding of nature was incomplete. It was a humbling and exhilarating moment, showing that even the most established theories have limits. Sometimes, a single anomaly can unlock an entirely new realm of understanding. The speed of light is constant in all frames of reference. Imagine riding a bike and tossing a ball. To someone standing still, the ball's speed is the speed of your throw, plus your bike. But now, imagine replacing the ball with a beam of light. According to Einstein, the speed of that light, 299,792,458 meters per second, doesn't add or subtract based on your motion. It stays constant no matter how fast you're moving. This defies all classical intuition. It means that no matter how fast you go, you can never catch up to a beam of light or make it go faster. This constant speed is not just a weird quirk, it's the cornerstone of special relativity. It forced physicists to accept a radical truth. Time and space themselves must adjust to keep the speed of light constant. Clocks tick slower, lengths shrink, and simultaneity becomes relative depending on your motion. This principle has been confirmed by countless experiments, from particle accelerators to GPS satellites. It's also one of the few constants woven into the very structure of our universe. More than a number, the speed of light is the foundation of modern physics, and the gateway to understanding how space and time are fundamentally linked. Time slows down the faster you go. Time dilation. What if someone could age more slowly just by moving faster? As strange as it sounds, this is exactly what Einstein's theory of special relativity predicts, and it's been proven. Time dilation means that for an object in motion, time literally ticks more slowly compared to someone standing still. The faster you move, the greater the effect. At everyday speeds, the change is tiny, unnoticeable, but near the speed of light, it becomes dramatic. An astronaut on a high-speed journey could return home to find that, while only a few years passed for them, decades passed for those they left behind. This is not science fiction, it's science fact. Atomic clocks flown on airplanes or orbiting Earth run slightly slower than those on the ground, confirming time dilation with high precision. GPS satellites must account for it to maintain accurate positioning. Time dilation has reshaped our concept of time itself. No longer is time absolute and universal. It's flexible, dependent on your speed through space. Time is not something we move through at a steady pace. It stretches and contracts depending on how we move. In the universe, motion and time are forever intertwined. Mass increases with speed. In the strange world of relativity, mass is not constant. It increases with speed. As an object moves faster and faster, especially as it approaches the speed of light, it becomes more resistant to acceleration. Its relativistic mass increases, meaning it takes more and more energy to keep speeding it up. This effect prevents any object with mass from reaching the speed of light. No matter how much energy you pump in, the object just gets heavier and heavier, never quite crossing that final barrier. This principle has profound implications. It's why particle accelerators, like the Large Hadron Collider, require immense energy to nudge particles just a little faster. It also leads us toward the equivalence of mass and energy, E equals mc squared. In some sense, the faster an object moves, the more energy it stores in the form of mass. This concept reframes mass not as a fixed property, but as something that responds to motion. It blurs the line between mass and energy, and reminds us that motion doesn't just bend time, it bends the nature of matter itself. Mass is not what it seems, it's a moving target. Nothing with mass can reach the speed of light. The speed of light isn't just fast, It's a cosmic speed limit. According to Einstein's theory of relativity, no object with mass can ever reach it. Why? Because as you accelerate something, its mass increases, and so does the energy needed to keep accelerating it. To reach the speed of light would require infinite energy, something the universe simply doesn't provide. This isn't a matter of better engines or technology. It's a fundamental limit built into the fabric of spacetime itself. This cosmic speed limit has shaped how we think about space travel, information transfer, and causality. If nothing can go faster than light, then information can't either. This preserves the order of cause and effect. It's why we can't instantly communicate with distant galaxies or travel to them quickly. But it's also a clue to something deeper, that light isn't just fast. It's tied to the structure of the universe. It defines how time flows and how space stretches. The limit doesn't just tell us what we can't do. It tells us how reality itself works. It's not a wall. It's a window into the rules that govern existence. Gravity is the warping of spacetime. General relativity. Gravity is not just a force pulling objects together. It's the bending of space and time around mass. This was Einstein's astonishing insight in his general theory of relativity. Massive objects like Earth or the Sun don't pull. They curve the very fabric of space-time, and other objects follow these curves. This model replaced Newton's force at a distance with a geometric picture. Planets orbit stars not because they're being pulled, but because they're moving through warped space-time. The bigger the mass, the greater the curvature. Light itself bends when it passes near a massive object, and time ticks more slowly deeper in a gravitational well. These predictions have been tested and confirmed. Light bends around stars, time dilation is measured by GPS satellites, and gravitational waves, ripples in space-time, have been directly observed. General relativity isn't just elegant, it's one of the most accurate theories ever created. It governs the orbits of planets, the structure of galaxies, and the behavior of black holes. It shows us that space isn't just emptiness, and time isn't just a ticking clock. Both are dynamic, flexible, and deeply influenced by mass and energy. Light bends around massive objects. One of the most mind-bending consequences of Einstein's general relativity is that light itself can bend, but it doesn't bend because something's pulling on it. It bends because space itself is curved. When light passes near a massive object, like a star or a galaxy, it follows the curvature of space-time created by that mass. The result is a phenomenon called gravitational lensing, where light from a distant source gets bent, magnified, or even split into multiple images by an intervening mass. This isn't theory. It's been observed and measured many times. The first dramatic confirmation came in 1919, when starlight was seen to shift position during a solar eclipse as it passed near the sun. Today, we use gravitational lensing to map dark matter, the invisible mass in galaxies, and to peer deeper into the cosmos than we otherwise could. Entire galaxies can act as lenses, creating natural magnifying glasses in the universe. What this tells us is profound. Light doesn't travel in straight lines through a neutral, empty space. It moves through a cosmic fabric that bends, stretches, and warps in response to mass. Space itself isn't passive. It's alive with geometry, and light is just following the curves. GPS satellites must account for relativity. You might think of Einstein's theories as abstract or theoretical, but they're part of your everyday life, quite literally. The GPS system that powers your smartphone relies on both special and general relativity to function accurately. GPS satellites orbit Earth at about 20,000 kilometers up, moving at around 14,000 kilometers per hour. Because of their speed, Special relativity says their onboard clocks tick slower than clocks on the ground, but because they're also farther from Earth's gravity, general relativity says time should tick faster for them than for us. These effects don't cancel out, they compound. The net result is that GPS satellite clocks tick about 38 microseconds faster per day than Earth-bound clocks. That may sound tiny, but it would cause GPS locations to drift by several kilometers per day if left uncorrected. Engineers must account for both types of time dilation when programming GPS systems, or else the entire system would quickly become useless. This is one of the most concrete proofs of Einstein's predictions. It also shatters any illusion that time is constant or absolute. Your sense of time depends on your speed and your position in the gravitational field. GPS doesn't just tell you where you are, it quietly reminds you that reality is relative. Gravity can cause time to move slower, gravitational time dilation. Time isn't fixed, it's elastic, and gravity can stretch or compress it. According to Einstein's general relativity, the stronger the gravitational field, the slower time flows. This is known as gravitational time dilation. It means that clocks tick more slowly near massive objects than they do farther away. The difference is measurable. In fact, atomic clocks placed just a few feet higher off the ground tick slightly faster than those closer to the Earth's surface. This isn't just a quirky side effect. It has real consequences. The closer you are to something massive, like a black hole, the more dramatic the time distortion. Near a black hole's event horizon, time could slow so drastically that a few minutes for you might equal years for someone far away. It's a concept that's been illustrated in films like Interstellar, but it's based on real physics. This phenomenon also helps explain why satellites need relativistic corrections. More than that, it changes how we think about time. Time isn't an invisible drumbeat guiding the universe. It's woven into the fabric of spacetime itself, stretching and compressing in response to mass and energy. In a very real sense, gravity shapes the pace of existence. Spacetime is like a stretched fabric. When Einstein described gravity as the warping of spacetime, he gave us a new mental image of the universe, one of spacetime as a kind of stretchy, flexible fabric. This metaphor helps us visualize how massive objects like stars and planets create dents in this fabric, and how other objects move through these curves. It's not a perfect analogy, but it works remarkably well for intuitive understanding. A heavy ball placed on a stretched sheet will deform it. A marble rolling nearby will spiral toward the ball, not because it's attracted, but because it's following the curve of the surface. Similarly, planets orbit stars because they're moving through curved spacetime. Even light follows these curves, but spacetime isn't made of anything physical. It's the stage upon which all physical processes occur. What Einstein showed is that the stage is not passive. It responds to mass and energy, and it can ripple, bend, stretch, and even vibrate, as we've seen in gravitational waves. This idea collapsed the distinction between space and time, combining them into a single, unified entity. It reframed the universe not as a backdrop, but as a dynamic player in the cosmic drama. E equals mc squared. Mass and energy are equivalent to Einstein's famous equation, E equals mc squared, is often quoted but rarely grasped in full depth. It means that mass and energy are not separate things. They are two forms of the same underlying reality. A small amount of mass contains an enormous amount of energy because the speed of light squared, c squared, is such a massive number. This equation explains why nuclear reactions are so powerful. In fission and fusion, a tiny fraction of mass is converted into an enormous release of energy. It powers the sun. It explains nuclear bombs. But the implications go far beyond that. E equals mc squared tells us that mass can be created from energy, and vice versa. In particle physics, high-energy collisions can create particles from pure energy. It also explains why particles gain mass as they accelerate. Their kinetic energy adds to their total energy, making them behave as if they have more mass. Philosophically, it collapses the distinction between matter and force, solid and invisible, substance and vibration. Mass is frozen energy. Energy is liberated mass. It's one of the most beautiful, compact, and far-reaching equations ever written, a single line that reveals the hidden unity of the universe. Matter and antimatter annihilate into pure energy. Every particle of matter in the universe, electrons, protons, neutrons, has a mirror twin called antimatter. An electron's antimatter counterpart is the positron, identical in mass but with opposite charge. When matter and antimatter meet, they annihilate in a flash of pure energy, typically in the form of high-energy photons, gamma rays. This interaction is one of the most efficient energy conversions known. 100% of the mass turns into energy, unlike chemical or nuclear reactions that only release a fraction. This phenomenon isn't just theoretical. It's observed in particle accelerators and PET scans in medicine, where positrons interact with electrons in your body, producing detectable gamma radiation. But antimatter holds a deeper cosmic mystery. The Big Bang should have produced equal amounts of matter and antimatter, yet our universe is almost entirely matter. Where did all the antimatter go? Why is there something instead of nothing? Scientists are still investigating this asymmetry, and solving it could unlock new physics. Antimatter also fuels speculative ideas like antimatter propulsion, promising energy-dense space travel. It's a reminder that for every building block of reality, there may be a shadow twin, identical, opposite, and devastatingly powerful. Quantum particles exist as probabilities. In classical physics, an object is where it is, doing what it's doing. But in quantum mechanics, particles don't have definite positions or velocities until we measure them. Instead, they exist as probability waves, mathematical descriptions of where they might be. A quantum particle, like an electron, isn't a tiny marble zipping through space. It's a cloud of possibilities, spread out across many potential locations. The equations of quantum mechanics, like the Schrödinger equation, describe this wave of probability, and when we observe or measure the particle, the wave collapses into a specific outcome. This behavior is strange and unintuitive, but confirmed in countless experiments. Electrons can interfere with themselves, tunnel through barriers, or appear in two places at once, until we look. This idea upends how we think about reality. It means nature is fundamentally indeterminate at its core. The world isn't made of tiny certainties, it's a shifting fog of possibilities. Our classical intuition fails here, replaced by a universe that only settles into certainty when we observe it. What happens in between? We don't fully know, but this probabilistic nature is the beating heart of quantum mechanics. Observation collapses the wave function. The phrase observation collapses the wave function sounds like science fiction, but it's a central concept in quantum mechanics. When a particle, like an electron, is unmeasured, it exists in a superposition, a blend of all possible states. It's not here or there, it's both. It's spinning up and down, traveling all paths. But when we measure it, when we interact with it in a way that forces a definite outcome, this wave function collapses. The electron chooses a single position, a single spin, a single reality. But what causes this collapse? Is it the measuring device? The consciousness of the observer? Is the wave function real, or just a tool for calculating probabilities? These are open questions. This phenomenon has been demonstrated in experiments like the double-slit experiment. Particles behave like waves when unobserved, but act like particles when measured. It's as if the act of looking creates reality, or at least chooses which version of it we get. This challenges the notion of an objective universe existing independently of observation. It suggests a more interactive cosmos, where reality isn't fixed until it's experienced. It doesn't just break our models, it breaks how we think about existence. The double-slit experiment shows light is both wave and particle. Imagine firing particles of light, photons, at a screen with two slits. Intuitively, you'd expect them to behave like little bullets, going through one slit or the other. But what you get is an interference pattern, a wave pattern, suggesting each photon goes through both slits and interferes with itself. Now, slow it down. Fire one photon at a time. Same result. The pattern builds up as if each photon spreads out, goes through both slits, interferes with itself, then lands in a single spot. This behavior isn't just for light. It happens with electrons, atoms, even molecules. If you place a detector at the slits to find out which slit the photon goes through, the interference disappears. It starts acting like a particle again. The act of measurement changes the outcome. This is the infamous wave-particle duality, and it shatters the classical view of the universe. Particles behave like waves. Waves act like particles. What something is depends on how we ask. The double-slit experiment is more than a physics demo. It's a portal into a deeper reality where observation shapes outcome and where things can be two contradictory things at once until we look. Heisenberg's uncertainty principle. You can't know both position and momentum. Heisenberg's uncertainty principle tells us that at the quantum level, certainty is an illusion. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a flaw in our measuring tools. It's a fundamental feature of reality. The act of measuring one quantity disturbs the other. Imagine trying to photograph a speeding car in complete darkness with a flash. The more precisely you time the flash, position, the harder it is to gauge its speed, momentum, and vice versa. But in the quantum world, this trade-off isn't just technical, it's built into nature. Electrons aren't tiny marbles with exact positions and velocities. They exist in a cloud of probabilities, and trying to pin down one aspect disturbs the other. This principle puts a hard limit on what can be known. It tells us the universe isn't made of fixed, predictable components, but of shifting, probabilistic fields. It also lays the groundwork for ideas like zero-point energy and quantum tunneling. Most importantly, it reminds us that the deeper we go, the fuzzier the lines become. Nature doesn't always give up her secrets all at once. Electrons exist in orbitals, not orbits. We used to imagine electrons orbiting the nucleus, like little planets around the sun. But this model doesn't hold up under quantum mechanics. Electrons don't follow precise paths. Instead, they exist in orbitals, mathematical regions where there's a high probability of finding them. These orbitals come in complex shapes, spheres, dumbbells, clovers, far from the tidy circles we once imagined. Electrons aren't little balls in motion. They're probability clouds. They're not located at one point, but smeared out across space. This discovery was revolutionary. It explained why atoms only absorb or emit energy in specific amounts, because electrons can only occupy certain quantized energy levels. This led to the development of quantum chemistry, which allows us to understand bonding, molecular structure, and reactions at the atomic level. Orbitals define how atoms combine into molecules, and how those molecules form the fabric of everything: water, DNA, stars, and you. It also means that atoms are mostly empty space. Your body is, in some ways, a cloud of probabilities. This shift in perspective, from orbits to orbitals, marks one of the biggest paradigm shifts in science, where location becomes likelihood, and certainty gives way to wave-based geometry. Tunneling allows particles to pass through barriers. Quantum tunneling is one of those effects that seems straight up impossible by classical logic. Imagine a ball rolling toward a hill. If it doesn't have enough energy to reach the top, it rolls back. Simple. But in the quantum world, particles sometimes pass through energy barriers they shouldn't be able to cross. Why? Because they're not just points. They're described by wave functions, and waves can stretch into and beyond barriers. If the wave on the far side isn't zero, there's a chance the particle can tunnel through. This isn't just theoretical. Quantum tunneling is real and measurable. It explains how the sun shines. Tunneling allows nuclear fusion to occur in conditions that classical physics says shouldn't be possible. It's used in scanning tunneling microscopes, allowing us to image atoms. It even underlies flash memory in your phone. Tunneling is also behind radioactive decay, where particles escape atomic nuclei. This phenomenon challenges the idea that particles are confined by barriers. In the quantum world, impossible often just means highly improbable, and every so often, the improbable happens. Tunneling reveals a reality where particles ghost through walls, not by breaking rules, but by following rules we're only beginning to understand. Quantum entanglement connects particles instantly. Einstein called it spooky action at a distance. Quantum entanglement is the bizarre phenomenon where two or more particles become linked in such a way that the state of one instantly affects the state of the other, no matter how far apart they are. Measure one particle's spin or polarization, and the other's value is instantly known, even if they're light years away. This seems to defy relativity, which says no information can travel faster than light. But entanglement doesn't transmit usable information. It just reflects a deep correlation built into the fabric of quantum systems. Experiments have confirmed this effect again and again, violating classical ideas of local realism. Entangled particles behave as a single system, no matter the distance between them. This isn't just a mind bender, it's useful. Quantum entanglement is the backbone of quantum computing, quantum cryptography, and potential ultra-secure communication systems. It suggests that the universe isn't a collection of separate local pieces. It's an interdependent web where things are deeply connected beyond space and time. Entanglement doesn't just connect particles, it connects us to a fundamental truth, that the universe may be more unified than our senses let on. Bell's theorem challenges local realism. Bell's theorem is one of the most profound and unsettling results in all of physics. In the 1960s, physicist John Bell proposed a testable way to distinguish between quantum mechanics and any theory that relies on local realism. The idea that information can't travel faster than light. and that physical properties exist before we measure them. Bell showed that if local realism were true, certain inequalities in experimental outcomes should always hold. But in real-world experiments, using entangled particles, these inequalities are violated. That means local realism doesn't describe reality. Either non-local connections are real, or properties don't exist until they're measured, or both. This result has been confirmed repeatedly. It means the universe is not just weird, it's fundamentally non-classical. Reality is not built from independent particles carrying pre-existing properties. Instead, measurement and entanglement create the outcomes we see. Bell's theorem shattered the comfort of classical assumptions. It tells us that any attempt to interpret quantum mechanics as a classical, hidden variable theory must abandon locality or realism, or both. It forces us to admit that the quantum world is not just strange, it's stranger than anything we were prepared for. Quantum superposition. A particle can be in multiple states at once. At the heart of quantum mechanics is superposition, the idea that a particle doesn't have to choose one state until it's measured. It can exist in multiple states at once, spinning both up and down, being in two places, or traveling two paths simultaneously. This idea is not metaphorical. It's mathematically real and experimentally confirmed. In the famous double-slit experiment, a single electron appears to interfere with itself, behaving like a wave going through two slits at once. In quantum computing, bits called qubits can be both 0 and 1 simultaneously, giving quantum machines their massive potential. Superposition is also the basis of the Schrödinger's cat thought experiment, where a cat in a sealed box is both alive and dead until someone opens it. It forces us to question what state even means. In a superposition, reality is not fixed. It's a set of probabilities. Only observation resolves it into one outcome. This isn't just science fiction. Superposition is used in quantum encryption, sensors, and early quantum computers. It's one of the clearest signs that the quantum world doesn't behave like ours. The universe, at its core, seems to prefer possibility over certainty until we come along and ask the question. Schrödinger's cat. Schrödinger's cat is a thought experiment that dramatizes one of quantum mechanics' strangest features, superposition. Imagine a cat placed in a sealed box. Inside the box is a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, the Geiger counter detects it, triggers the hammer, and breaks the vial, killing the cat. If the atom doesn't decay, the cat lives. But quantum mechanics says the atom is in a superposition of decayed and undecayed states until it is observed. That means the cat is also in a superposition, both alive and dead, until someone opens the box. Schrödinger didn't propose this to suggest zombie cats are real. He meant it as a critique of the Copenhagen interpretation of quantum mechanics. The point is this: when does quantum indeterminacy stop and classical reality begin? Does observation cause the wave function to collapse? If so, what counts as an observer? A human? A measuring device? The cat itself? Schrödinger's cat sits at the crossroads of physics and philosophy, showing how our classical intuition fails in the quantum realm. It forces us to confront a question we still don't have an answer to. What is the role of consciousness in collapsing reality? Quantum decoherence. Quantum decoherence is the real-world mechanism that explains why we don't see cats that are both alive and dead in everyday life. It describes how quantum superpositions interact with the environment, causing them to lose their quantumness and appear classical. Imagine a quantum system, say a particle in a superposition of two states. As soon as it interacts with the outside world, air molecules, photons, anything, it becomes entangled with that environment. The information about its superposition leaks into the surroundings, and from our point of view, the system seems to have picked a state. Decoherence doesn't collapse the wave function like in the Copenhagen view. It explains why it looks like it did. The cat was never truly in two states from your perspective because the environment already forced a kind of collapse before you opened the box. Decoherence is essential in quantum computing, where we must isolate qubits to keep them coherent and functional. It also bridges quantum and classical physics, showing how the weirdness of the quantum world disappears as systems grow and interact. Decoherence doesn't solve every mystery, but it's a powerful step toward understanding why our world looks stable, definite, and sensible, even though it's built from uncertainty. Bose-Einstein condensates matter as a single wave. At temperatures close to absolute zero, something magical happens. A group of particles called bosons, which can occupy the same quantum state, begin to overlap. Their individual identities vanish, and they behave as one unified quantum entity. This is a Bose-Einstein condensate, BEC, first predicted by Satyendra Nath Bose and Albert Einstein. In this state, matter stops behaving like discrete particles and starts acting like a single, giant wave function. Beck's let us observe quantum behavior at a macroscopic level. Ripples, interference patterns, and quantum coherence, all in a visible clump of atoms. They're so delicate, they can be disrupted by the slightest heat or noise, but when isolated, they offer a playground to study superfluidity, quantum vortices, and matter-wave duality. BCs don't just reveal strange new physics, they give us direct access to the quantum ground state of matter. It's like cooling reality down to its most fundamental rhythm. In a way, they make tangible the idea that the universe isn't made of particles bouncing around like marbles. It's made of waves, and under the right conditions, those waves sync up and sing in perfect harmony. Fermions versus bosons. Two families of everything, all particles in the universe, fall into one of two camps, fermions or bosons. This classification is foundational in quantum physics. Fermions, like electrons, protons, and neutrons, obey the Pauli exclusion principle, which means no two can occupy the same quantum state. They make up matter. They're what give atoms their structure, what makes objects solid, what gives rise to everything from chemistry to your skin. Bosons, on the other hand, like photons, gluons, and the Higgs boson, can all occupy the same state. In fact, they love to pile up. That's why lasers, which consist of photons all in the same state, exist. Bosons are force carriers. They're what allow particles to interact, to attract or repel. The simple split, fermions make stuff, bosons make stuff interact, builds the whole universe. The difference comes down to a property called spin. Fermions have half-integer spin, 1/2, negative, 1/2. Bosons have whole number spin, 0, 1, 2. From that tiny mathematical detail emerges the grand architecture of reality. Understanding fermions versus bosons is like understanding yin and yang. You need both form and connection, identity and relationship for anything to exist at all. Pauli exclusion principle. Why matter has structure. The Pauli exclusion principle, proposed by Wolfgang Pauli in 1925, says that no two identical fermions can occupy the same quantum state at the same time. This single rule explains why atoms have structure, why matter doesn't collapse into a uniform blob, and why the universe doesn't look like a featureless soup. Electrons in an atom fill up different orbitals, 1s, 2s, 2p, and so on, because of this principle. Each level can hold only a limited number of electrons, forcing them into distinct shells. This gives rise to the periodic table, chemical behavior, and the diversity of materials. The exclusion principle is also why white dwarf stars don't collapse completely. The electrons inside resist being squeezed too close. This resistance is called degeneracy pressure, and it balances gravity. The same is true for neutron stars, where neutrons take on the same role. Pauli's principle isn't just a detail, it's the backbone of matter's identity. Without it, there'd be no complexity, no chemistry, no life. Every element, every bond, every stable structure in the universe exists because nature says, this spot is taken. The Standard Model of Particle Physics. The Standard Model is our best description of the fundamental building blocks of nature. It explains all known particles, quarks, leptons, bosons, and the forces that govern them, except gravity. It's like a periodic table of the subatomic world. There are 6 quarks, 6 leptons, including the electron and neutrinos, and a family of force carriers. The photon, electromagnetism, W and Z bosons, weak nuclear force, gluons, strong nuclear force, and the Higgs boson, mass. The Standard Model has been wildly successful in predicting particles before we observe them, like the top quark and the Higgs boson. Its equations power particle accelerators, explain fusion in stars, and describe why matter clumps into atoms. But it's also incomplete. It doesn't include gravity, dark matter, or the accelerating expansion of the universe. It has more than 20 constants that we can't explain, only measure. Still, it's one of science's greatest achievements. If the Standard Model is a puzzle, we've found the edge pieces and the corners, but we're still searching for the full picture. The 4 fundamental forces. Everything in the universe is governed by just 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each one has its own character. Gravity pulls things together. It holds planets in orbit and shapes galaxies. Electromagnetism governs electricity, magnetism, and light, responsible for everything from cell phones to lightning. A strong force holds atomic nuclei together. Without it, protons would repel each other, and atoms would fall apart. The weak force enables radioactive decay and nuclear fusion in the sun. Each force has its range, strength, and carrier particles. Gravity is the weakest, but acts across infinite distance. The strong force is the strongest, but only works at subatomic scales. These 4 forces seem very different, but many physicists believe they may all be unified under a deeper theory. Just like electromagnetism once unified electricity and magnetism. The quest to unify the 4 forces has driven physics for decades. Until we do, these 4 remain the rulers of everything from the tiniest quarks to the largest clusters of galaxies. Quarks and leptons, the building blocks of everything. All known matter is made from two families of particles, quarks and leptons. Quarks combine to form protons and neutrons, while leptons include the electron and its cousins. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. They're never found alone, thanks to confinement, but instead combine in groups of 2 or 3. Protons, for example, are made of 2 up quarks and 1 down. Leptons are loners. Electrons are stable and found in atoms, while neutrinos are ghost-like particles that barely interact with matter. These 12 particles, 6 quarks, 6 leptons, form the basic alphabet of the universe. All the chemistry, biology, and astronomy we know comes from how they interact via the fundamental forces. Despite their tiny size, their behavior shapes everything, and they might not be the end. Some theories propose even smaller constituents, or that quarks and leptons are part of a higher dimensional framework. But for now, they are the bricks and mortar of reality. Higgs boson. Why particles have mass. The Higgs boson is the quantum of the Higgs field, an invisible field that fills the universe. Some particles, like photons, pass through it untouched. They remain massless. Others, like W and Z bosons, interact with it strongly and thus gain mass. This field is essential to the Standard Model. Without it, all particles would be massless and atoms couldn't form. The discovery of the Higgs boson in 2012 confirmed a decades-old prediction, earning a Nobel Prize and completing the Standard Model. But the Higgs is more than a checkmark. Its field defines the mass scale of the universe. It's also tied to deep puzzles, like why the universe didn't collapse after the Big Bang, or why the Higgs mass is so low compared to what quantum theory predicts. The Higgs boson isn't just a particle. It's the key to why stuff feels solid, why inertia exists, and why we can exist at all. Quantum vacuum. Empty space isn't empty. In classical physics, a vacuum is nothingness. But in quantum physics, the vacuum is a roiling sea of activity. Thanks to Heisenberg's uncertainty principle, even empty space teems with virtual particles that briefly pop in and out of existence. These fluctuations give rise to measurable effects like the Casimir effect, where 2 metal plates in a vacuum attract due to pressure differences in the quantum field. The vacuum also holds 0-point energy, a baseline level of energy that can't be removed. This energy might be connected to dark energy and the expansion of the universe. Some theories even suggest that entire universes could emerge from vacuum fluctuations. The quantum vacuum challenges the very idea of nothingness. Space isn't an empty container. It's an active participant in reality. It seethes with possibilities, constantly shaping what can happen next. Even in total silence, the vacuum hums. Quantum field theory. Particles are fields in disguise. Quantum field theory, QFT, is one of the most powerful and accurate frameworks in all of physics. It's the theory that unites quantum mechanics with special relativity and redefines what particles are. In quantum field theory, particles aren't tiny dots flying through space. They're excitations in invisible fields that permeate the universe. There's a field for electrons, a field for photons, a field for quarks, and what we call a particle is just a ripple in that field. The quantum rules apply to the field itself. It fluctuates, it superposes, it interacts with other fields. When two electrons repel, it's not magic. It's the electron field interacting with the photon field. QFT gives rise to the Standard Model, predicts particle behaviors with astonishing precision, and explains why atoms and forces work the way they do. It's used in particle colliders, quantum electrodynamics, and even explains how the vacuum isn't empty. But QFT is not intuitive. It suggests reality isn't made of stuff, but of energy patterns in invisible fields. Everything solid, visible, and touchable is just a vibration in an invisible mathematical ocean. Quantum electrodynamics, QED. The most accurate theory ever. Quantum electrodynamics, or QED, is a quantum field theory that describes how light and matter interact. Specifically, it explains how electrons and photons exchange energy through electromagnetic forces. This theory was developed by Richard Feynman, Julian Schwinger, and others, and it combines quantum mechanics, special relativity, and field theory into one coherent framework. QED's power lies in its precision. It can calculate the magnetic moment of the electron to 11 decimal places, and it matches experiment exactly. Nothing else in science is that accurate. QED introduced a new kind of math based on Feynman diagrams, where interactions are visualized as wavy lines and particle paths, like electrons emitting and reabsorbing virtual photons. These interactions, though they look simple, encode deep layers of reality. Particles appear and vanish in the vacuum, fields exchange energy constantly, and probabilities replace certainties. QED not only explains why light bounces off mirrors or how atoms emit radiation, it also laid the foundation for quantum computers, semiconductors, lasers, and all of modern electronics. At its heart, it describes the dance between light and charged particles, a fundamental rhythm of the cosmos, performed with unfailing accuracy. Quantum chromodynamics, the theory of quarks and gluons. Quantum chromodynamics, QCD, is the theory that describes the strong nuclear force, the force that holds protons and neutrons together in the nucleus. Unlike gravity or electromagnetism, this force works through color charge, and the particles that carry it are quarks, which make up protons and neutrons, and gluons, which bind the quarks together. The word color here has nothing to do with visible color. It's a metaphor for a property that quarks carry. What makes QCD so bizarre is that the more you try to pull quarks apart, the stronger the force becomes, like stretching a rubber band that never breaks. Eventually, you'll just create new quark-antiquark pairs. This is why we never observe free quarks in nature. They're always confined in groups. Gluons themselves also carry color charge, which means they can interact with each other, making the strong force incredibly complex. QCD is essential to understanding atomic structure, nuclear decay, particle collisions, and the conditions of the early universe. It's part of the Standard Model, but also a frontier, because we still don't have a perfect handle on its math. It's a reminder that even inside the atom, nature's rules are wild, tangled, and not yet fully known. Renormalization tames infinities in quantum field theory. Quantum field theories are astonishingly powerful, but when you start calculating with them, strange things happen. You often get infinite answers, especially when dealing with particles interacting at very small scales. That's a big problem. Infinities don't make sense in physical reality. Enter renormalization, a mathematical technique that allows physicists to remove these infinities and produce finite, testable predictions. It works by redefining quantities like mass and charge in terms of what we actually observe. Think of it like zooming in on a fractal. Things look chaotic and undefined up close, but when you step back, a clean pattern emerges. Renormalization smooths out the chaos, letting us recover meaningful numbers from infinite equations. It turned quantum electrodynamics from an elegant failure into the most accurate theory ever. Later, it helped with QCD and even parts of condensed matter physics. Some critics once called renormalization a mathematical trick, but it's more than that. It's a profound insight. Nature might be messy at small scales, but physics still works when you ask the right questions. Renormalization reminds us that the laws of nature aren't always clean underneath, but they're still consistent at the scale we live in. Quantum gravity, we don't have a working theory, yet one of the biggest missing pieces in modern physics is a full theory of quantum gravity, a way to unite general relativity, which governs massive objects and curved space-time, with quantum mechanics, which rules the tiny world of particles and fields. Right now, these two frameworks are both incredibly successful on their own, but they don't agree with each other. Try to apply quantum rules to a black hole, and things fall apart. Try to quantize space-time itself, and you hit mathematical walls. Efforts like string theory and loop quantum gravity are promising, but so far, no theory has been experimentally confirmed. The stakes are high. A quantum theory of gravity could explain what happens inside black holes, what occurred at the moment of the Big Bang, or why the universe expands the way it does. It could also finally answer whether space-time is continuous or made of tiny, discrete units. Quantum gravity isn't just a holy grail for physicists. It's a clue that our current understanding is incomplete. Somewhere out there, the next major breakthrough is waiting. Until then, gravity remains the last great frontier of unification. Gravity may be emergent, not fundamental. What if gravity isn't a fundamental force like we've always thought? What if it emerges from deeper laws, just like temperature emerges from the motion of particles? This is the radical idea behind emergent gravity. Some physicists propose that gravity is not a basic ingredient of the universe, but the result of statistical behavior of microscopic degrees of freedom, like information or quantum entanglement between particles. This is inspired by how thermodynamics works. We don't see temperature particles, but temperature still exists because of collective motion. Similarly, gravity could emerge from the way information is encoded on the fabric of space-time. One version, proposed by Eric Verlinde, suggests that gravity is an entropic force, a byproduct of the universe trying to maximize entropy. If true, this would overturn general relativity as a fundamental theory and explain dark matter effects without needing invisible particles. While still unproven, emergent gravity would recast our view of space, time, and mass, not as building blocks, but as emergent illusions from something more basic. It suggests we've been mistaking the shadow for the source, and gravity may be a side effect of something deeper we haven't yet seen. The holographic principle. Reality may be 2D. The holographic principle is one of the most mind-shattering ideas in modern theoretical physics. It suggests that everything we experience in 3D space, planets, people, even your own body, might be a projection of information encoded on a distant 2D surface, like a hologram. This concept arose from attempts to solve the black hole information paradox. Physicist Jacob Bekenstein found that a black hole's entropy, its information content, is proportional not to its volume, but to its surface area. That means all the information inside a region might be stored on its boundary. Leonard Susskind and others extended this to the entire universe. It suggests that the entire three-dimensional world could be the result of quantum information encoded on a two-dimensional cosmic screen at the edge of space-time. The math behind this is deep and still developing. But if true, it means our experience of depth, motion, and reality could be a kind of illusion, a projection from a lower dimensional truth. The holographic principle blurs the boundary between physics and metaphysics and forces us to question, is the universe real or just information playing out on a cosmic canvas? Black hole entropy, area, not volume. Black holes are often thought of as cosmic vacuum cleaners, massive objects that trap everything, even light. But they're also thermodynamic objects. They have temperature, they radiate energy via Hawking radiation, and crucially, they have entropy. In 1973, Jacob Bekenstein proposed that a black hole's entropy is proportional to the area of its event horizon, not its volume. That was shocking because most things, like gases, have entropy that scales with how much space they take up. But black holes? Their information content is somehow stored on the 2D surface of the event horizon. Stephen Hawking later confirmed this by showing that black holes emit radiation, which implies they have a temperature and therefore entropy. This discovery links gravity, thermodynamics, and quantum theory into a single idea, and it's one of the strongest hints we have that space itself might be built from information. It also laid the groundwork for the holographic principle and modern black hole physics. Black hole entropy suggests that what you see inside the universe may not be the full story. The truth might lie on the boundary where space folds into information and entropy holds the key. Hawking radiation. Black holes aren't eternal. For decades, black holes were thought to be inescapable prisons of matter and light. But in 1974, Stephen Hawking showed that, thanks to quantum effects, black holes aren't completely black. They glow. This phenomenon is called Hawking radiation, and it arises from virtual particles at the edge of the event horizon. Normally, these particles annihilate each other instantly, but if one falls into the black hole and the other escapes, it looks like the black hole is emitting energy. Over time, this radiation causes the black hole to lose mass and shrink. In theory, if left alone long enough, a black hole would evaporate completely. This was a radical idea. It turned black holes into thermodynamic systems with lifespans rather than eternal traps. But it also triggered the information paradox. If a black hole evaporates, what happens to the information about what fell in? Quantum mechanics says information can't be destroyed, but Hawking radiation seemed to erase it. This paradox still isn't fully solved, but it reshaped our understanding of black holes, from final destinations to dynamic, evaporating bridges between gravity and quantum theory. It's one of the biggest mysteries in physics today. The black hole information paradox. Here's the problem. If you throw something into a black hole, say a book, it seems like that information is lost forever, but quantum mechanics forbids information destruction. Even if the book is shredded, burned, and atomized, the information should still exist in principle. When Stephen Hawking showed that black holes emit Hawking radiation and eventually evaporate, he raised a troubling question. If the black hole disappears, where does the information go? Is it smeared into the radiation? Is it trapped in a hidden remnant? Or is it just gone? This contradiction between quantum mechanics, which says information is preserved, and general relativity, which seems to allow its destruction, is the black hole information paradox. It's not just a technical glitch, it's a clash of worldviews. Solving it could require a full theory of quantum gravity. Some proposals suggest information is encoded in subtle correlations in the Hawking radiation. Others say it's stored on the event horizon via the holographic principle. Some theories even hint that spacetime itself remembers. Whatever the answer, it will change how we think about entropy, time, and even reality itself. Because if information can be truly lost, so can causality. String theory. Particles as vibrating strings. What if all the particles in the universe, the electrons, quarks, photons, aren't point-like dots but tiny vibrating strings? That's the core idea of string theory. These strings are unimaginably small, about the size of the Planck length, 10 to the negative 35th power meters, and their vibration modes determine what kind of particle they appear as. One vibration might be an electron, another a graviton. In this way, all forces in matter could be unified as different expressions of the same fundamental object. String theory isn't just elegant, it solves a major problem: how to include gravity in quantum mechanics. In traditional quantum field theory, gravity doesn't fit. It causes infinities and breakdowns. But string theory naturally includes a particle that looks exactly like the graviton, the theoretical quantum carrier of gravity. That's why physicists take it seriously. But there's a cost: extra dimensions. String theory only works in 10 or 11 dimensions, most of which are compacted or curled up at microscopic scales. These extra dimensions are where the complexity and the beauty lives. They could determine the laws of physics we observe, like a cosmic blueprint. So far, string theory hasn't made testable predictions we can measure, but as a unifying framework, it's one of our best leads toward a theory of everything. If it's right, the universe isn't made of particles, it's made of music, played on a multidimensional violin. Extra dimensions. More than meets the eye. We experience the world in 3 spatial dimensions and 1 time dimension. But what if there are more, hidden dimensions curled up so tightly that we can't detect them? String theory requires extra dimensions, not as a bonus, but as a necessity. It can't function in 3D space alone. The math only works when there are 10 or 11 dimensions, depending on the version. How does that make sense? Think of a garden hose. From far away, it looks like a line, 1D. But up close, you see it's a tube with a small circular extra dimension wrapped around it. Similarly, the universe could have tiny, compactified dimensions that exist at every point in space, but are so small we don't perceive them. These hidden dimensions might control the behavior of particles, the strength of forces, or even the values of fundamental constants. Some physicists speculate that gravity is weaker than the other forces because it spreads into extra dimensions, while electromagnetism and the strong force are stuck in our 3-dimensional world. This could explain why gravity is so much weaker than, say, electromagnetism, why a fridge magnet can lift a paperclip against the pull of the whole Earth. If extra dimensions exist, they could be probed indirectly through particle accelerators, gravitational waves, or subtle effects in cosmology. They would mean that everything we see, galaxies, atoms, space itself, is just a slice of a larger, richer reality. Brains. The universe as a membrane in higher space. In string theory's more advanced version, called M-theory, not only do we have strings, we also have higher dimensional objects called brains, short for membranes. A brain can be 1D like a string, 2D like a sheet, or even higher, up to 10 spatial dimensions. These objects don't just exist in space, they are space. In fact, our entire universe might be a 3D brain floating in a higher dimensional bulk. Think of a soap film suspended in the air. That's our universe, and the air around it is the higher dimensional space. Particles like electrons and quarks could be vibrations confined to the brain, while gravity might be the only force able to leak into the higher dimensional bulk. This would explain why gravity is so weak. It's diluted across more dimensions. Brain theory also opens wild possibilities. If other branes exist in the bulk, they could be parallel universes, each with its own laws of physics. In some cosmological models, the Big Bang was caused by two branes colliding and releasing energy. That means our universe wasn't born from nothing. It was sparked by contact in a higher dimensional arena. M-theory and its brain world picture might be the best path to uniting quantum mechanics with gravity. But more than that, it shows us that space itself might be a living, dynamic object, stretching and interacting in ways our 3D minds can barely imagine. Supersymmetry, a shadow particle for everything. Supersymmetry, or SUSY, is a proposed extension of the Standard Model that doubles the number of fundamental particles. For every known particle, like the electron, quark, photon, there's a superpartner, the selectron, squark, photino, and so on. These partners haven't been observed yet, but they solve some serious problems in physics. First, they help stabilize the mass of the Higgs boson, preventing it from being blown up to infinite values by quantum corrections. Second, they could unify the strengths of the fundamental forces at high energies. And third, and perhaps most compelling, the lightest supersymmetric particle might be the dark matter that fills our universe. That's right. SUSY could explain what 85% of the universe is made of. SUSY also fits neatly into string theory. Without it, string theory falls apart mathematically. It brings elegance and balance to the particle zoo, suggesting nature has a hidden symmetry between matter and force. Just like how electromagnetism unified electric and magnetic fields, SUSY could unify particles and their interactions under a deeper framework. But there's a catch. We haven't found any superpartners yet. Particle accelerators like the LHC have been searching, and while hints appear, nothing definitive has surfaced. Still, many physicists believe SUSY, or something like it, is lurking just beyond our current reach. Supersymmetry whispers that the universe we know is only half the story, and its twin, perfectly mirrored, is waiting to be discovered. M-theory, the mother theory of everything. M-theory is the ambitious, still mysterious framework that unifies all 5 versions of string theory into a single, deeper theory. It emerged in the mid-1990s when physicists realized the different string theories weren't rivals, they were different perspectives of the same thing. Like blind men describing parts of an elephant, each version told part of the story. M-theory brought them together. It requires 11 dimensions, 10 of space, 1 of time, and replaces strings with supermembranes, or branes that can have multiple dimensions themselves. It includes gravity, explains black hole entropy, fits the Standard Model, and even allows for a multiverse of parallel brane worlds. But here's the twist. No one knows exactly what M-theory is. We don't yet have a full mathematical description. It's more of a framework, a guiding light toward the ultimate theory of everything. It's where quantum mechanics, gravity, extra dimensions, and supersymmetry all converge. If M-theory is correct, it would complete a journey that began with Newton's apple, from falling objects to curved spacetime to vibrating strings and membranes in 11 dimensions. It's the boldest idea we've ever conceived. It may sound like science fiction, but it's built from math, consistency, and the relentless pursuit of truth. M-theory says, we've only scratched the surface of the real universe. The multiverse theory, infinite universes with different laws. What if the universe isn't the universe at all, but just one of countless others? That's the idea behind the multiverse theory, the notion that there isn't one cosmos, but a vast collection, perhaps an infinite set of universes, each with its own physical laws, particles, and dimensions. There are several versions of the multiverse. One comes from inflationary cosmology. the idea that our universe rapidly expanded in the Big Bang. Some theories suggest inflation never stopped in the bigger picture. Instead, bubble universes constantly form, each with its own version of physics. That's called eternal inflation. Another version comes from string theory, which allows for many different solutions to its equations, each describing a different possible universe, known as the landscape. Still another comes from quantum mechanics. If every quantum event splits reality into multiple outcomes, then perhaps every possibility exists in some version of the multiverse. This theory isn't just wild imagination. It tries to explain why our universe seems so finely tuned for life. Maybe we just happen to live in the one that works. The multiverse is controversial because it's hard, maybe impossible to test. But if it's true, we are just one note in a cosmic symphony without end. The anthropic principle. We see this universe. Because we can. Why does the universe seem perfectly tuned for life? Why do the constants of nature, gravity's strength, the charge of the electron, the mass of the proton fall within the narrow range that allows stars, chemistry, and consciousness? That's the puzzle the anthropic principle tries to address. At its core, the anthropic principle says, we see the universe the way it is because we're here to see it. If the universe had different constants, we wouldn't be around to ask the question. In other words, our very existence filters the types of universes we can observe. This idea is deeply tied to the multiverse. If there are infinite universes with different properties, it's not surprising we find ourselves in one that allows life. There are different versions of the principle. The weak anthropic principle is fairly uncontroversial. It just acknowledges selection bias. But the strong version suggests that the universe must allow conscious observers to emerge, as if life is a required feature of reality. To some, the anthropic principle feels like a cop-out. To others, it's a powerful philosophical insight that consciousness plays a role in shaping what kind of universe is relevant. Whether you love it or hate it, the anthropic principle reminds us we're not just studying the universe, we're inside it, and that fact may change everything. Cosmic inflation, the universe's sudden growth spurt. Right after the Big Bang, the universe didn't just expand, it inflated. In less than a trillionth of a second, it ballooned from subatomic size to something the size of a grapefruit, or even larger. This theory, called cosmic inflation, explains many of the deepest puzzles in cosmology. Why is the universe so smooth and uniform across vast distances? Why is it flat rather than curved? Why don't we see magnetic monopoles or other exotic relics? Inflation solves these problems in one swoop. It stretches tiny quantum fluctuations into vast cosmic structures, seeding the formation of galaxies and cosmic microwave background (CMB) ripples we observe today. Proposed by Alan Guth in the 1980s, inflation has become a central part of Big Bang cosmology. Its predictions match what we see in the CMB with stunning accuracy, but we still don't know exactly what field caused inflation or how it ended. Some models suggest inflation never truly stops. It keeps spawning pocket universes, each with different physics. That's where it merges with multiverse theory. Inflation is a cosmic growth spurt with universe-defining consequences. It shows us that what happened in the first blink of time may explain everything that followed. The Big Rip, the universe may tear itself apart. We know the universe is expanding, and that expansion is accelerating. But what if it never slows down? What if it keeps accelerating forever? That's the terrifying idea behind the Big Rip, a possible future where dark energy becomes so dominant that it tears the universe apart. Right now, galaxies are drifting away from each other because of dark energy. But if dark energy's strength grows over time, in what's called a phantom energy model, it will eventually overpower all other forces. First, it will pull apart galaxy clusters, then individual galaxies, then solar systems, then atoms. In the final moments, even subatomic particles would be ripped apart as the fabric of spacetime itself shreds. The Big Rip timeline depends on how dark energy behaves. If its equation of state crosses a certain threshold, this fate could happen in tens of billions of years, or sooner, in more extreme models. This isn't just cosmic horror, it's a reminder that the universe has multiple possible fates. It may end in heat death, a big crunch, a bounce, or a rip. We don't know which is correct, but each scenario reveals something profound, that the cosmos is not static, and that time may carry all things, not toward peace, but toward unraveling. Loop quantum gravity, quantizing space-time itself. Loop quantum gravity, LQG, is an alternative to string theory, and instead of unifying all forces, it focuses solely on reconciling quantum mechanics with general relativity. In LQG, space and time aren't continuous. They're made of tiny discrete loops that form a kind of woven network, like a quantum fabric. Imagine space not as a smooth, empty stage, but as a pixelated structure. These loops are incredibly small, on the order of the Planck length, but they make up everything. Geometry itself becomes quantized. Areas, volumes, and even time intervals come in tiny, indivisible units. This model avoids the infinite densities of black holes and the Big Bang. Instead of a singularity, LQG predicts a big bounce. A previous universe collapsed and rebounded into the one we see today. It also provides a framework to study black hole entropy without needing extra dimensions or strings. LQG is still in development and lacks the unifying elegance of string theory, but it's conceptually radical. It says that space itself is made of quantum stuff, and that gravity is a byproduct of how this space bends and twists. If it's right, the smoothness of space is just an illusion. The universe, like matter and energy, may be woven from quantized threads. Planck length, the smallest meaningful unit of space. What's the smallest possible distance in the universe? Not just the tiniest thing we've measured, but the smallest that can exist in principle? That's the Planck length, about 1.6 times 10 to the negative 35th meters, smaller than atoms, protons, or even quarks. It's so small it makes a proton look like the size of the galaxy in comparison. The Planck length isn't just a random number. It's derived from three fundamental constants: the speed of light, Planck's constant, and the gravitational constant. It's the scale where quantum mechanics and gravity become equally important, where space-time is expected to break down into a quantum foam of fluctuations. Below the Planck length, the very concept of distance may no longer make sense. Geometry itself could cease to be smooth. That's why many physicists believe it marks the limit of measurable reality, a kind of cosmic pixel size for space. Loop quantum gravity and string theory both rely on this scale as the boundary of meaningful physics. The Planck length reminds us that the universe is not infinitely divisible. There's a lower limit, a grain to space itself. Zoom in far enough, and space becomes not a smooth fabric, but a quantized structure beyond imagination. The Big Bounce, a universe that cycles forever. What came before the Big Bang? One radical idea says, another universe. According to the Big Bounce theory, our universe didn't start from nothing. It began when a previous universe collapsed in on itself, rebounded, and began expanding again. And it might happen over and over, an eternal cosmic cycle. In traditional Big Bang cosmology, the beginning of the universe is a singularity. a point of infinite density and zero volume. But infinite quantities are a red flag. They usually signal that a theory has reached its limit. That's where quantum gravity theories come in. Both loop quantum gravity and some string theory cosmologies suggest that space-time can't shrink below a certain size, like a spring compressed to its limit. When it hits that quantum limit, it rebounds. Bang becomes bounce. In this view, our universe is part of an eternal rhythm: expansion, contraction, bounce, repeat. Each cycle could have different physics, different constants, maybe even different dimensions. The big bounce replaces the concept of a one-time creation with something deeper, a universe that is reborn endlessly with no true beginning or end, just transformation. Wormholes, shortcuts. Through space-time. Wormholes are theoretical tunnels that connect two distant points in space-time, like shortcuts through the universe. First predicted by Einstein and Rosen as Einstein-Rosen bridges, wormholes arise naturally from the equations of general relativity. If real, they could allow faster-than-light travel without violating the cosmic speed limit, by bending space instead of crossing it. Imagine folding a piece of paper so that two distant points touch, then poking a hole between them. That's the idea. Wormholes could, in principle, let you travel from one side of the galaxy to the other in moments, or even from one universe to another. But there's a catch, or many. Wormholes require negative energy to stay open, something called exotic matter. Without it, the tunnel collapses instantly. We've never observed exotic matter in stable quantities. Also, quantum effects may destabilize any wormhole that forms. Still, wormholes fascinate physicists, not just for travel, but because they connect general relativity with quantum mechanics, black holes, and even entanglement. Some theories suggest black holes might contain wormholes, or that the fabric of space itself is held together by tiny quantum wormholes. They remain theoretical, but if wormholes exist, they could offer not just travel, but a window into the true structure of reality. Closed time-like curves, time travel within physics. Imagine a path through space-time that loops back on itself, a route where, if you follow it long enough, you end up before you started. This is the idea of a closed time-like curve, CTC, a solution to Einstein's equations that allows time travel to the past, mathematically at least. Some rotating black holes, like the Kerr solution, or certain configurations of space-time, like Gödel's rotating universe, allow these loops in time. They don't require breaking the laws of physics, just bending them in extreme ways. In a CTC, a particle, or a person, could travel along a curved path through space-time and return to their own past. But this opens the door to paradoxes. What happens if you prevent your own birth, or give yourself the answer to a problem you haven't solved yet? These paradoxes challenge causality and logic. Some physicists believe that quantum effects or chronology protection will ultimately prevent closed time-like curves from forming. Others explore them as serious possibilities in advanced space-time geometries. Regardless, they raise deep questions about time, determinism, and the structure of the universe. CTCs force us to consider, what is time, really? And are we moving through it? Or is it looping behind our backs? Tachyons, hypothetical faster than light. Particles. According to relativity, nothing can accelerate to the speed of light. But what if something always traveled faster than light? Such hypothetical particles are called tachyons. First proposed in the 1960s, tachyons would break many of our intuitions. They'd have imaginary mass, lose energy as they speed up, and could, in theory, allow information to travel backward in time. Tachyons have never been observed, and many physicists believe they don't exist because their presence could violate causality and lead to paradoxes. But in certain mathematical frameworks, especially quantum field theory and string theory, tachyon-like entities do appear. They often indicate instability, not real particles, like a signal that the system wants to shift into a lower energy state. In speculative theories, tachyons remain fascinating. If they existed, they could upend relativity, enable faster-than-light communication, or even link quantum entanglement to space travel. But they might also destroy our ability to make sense of cause and effect. Whether real or not, tachyons push us to test the boundaries of what we consider possible. They ask, if the universe has a speed limit, is it truly unbreakable, or just a rule we haven't learned how to bend yet? Vacuum metastability. The universe could collapse at any moment. You're sitting in what you think is empty space, but what if that space is unstable? According to quantum field theory, our universe may exist in a false vacuum, a low energy state that seems stable, but isn't the true lowest energy configuration. If this is the case, then at any moment, a quantum fluctuation could kick space into its true vacuum state, triggering a vacuum decay event. This would create a bubble of real vacuum that expands at light speed, rewriting the laws of physics inside it. Atoms would disintegrate, time would distort, and everything we know, matter, chemistry, even the structure of space, would cease to exist. No warning, no escape. It sounds like science fiction, but it's a real possibility. Calculations involving the mass of the Higgs boson and top quark suggest we may be on the edge of instability. We live in a precarious balance. Now, this doesn't mean we're doomed. The timescale for such a collapse might be trillions of years, or never. But the fact that it's possible reminds us the vacuum isn't nothing. It's a dynamic, active field. And the universe, even at its calmest, may be balancing on a cosmic knife's edge. Emergent spacetime. Space and time aren't fundamental. What if space and time aren't the backdrop of reality, but emergent illusions like temperature or pressure? That's the idea behind emergent spacetime, the concept that space and time aren't fundamental. They arise from more basic quantum ingredients like entanglement, information, or quantum states. In this view, spacetime is not the stage, it's the play. The deeper level could be made of quantum bits, strings, or something we haven't discovered yet. When enough of these components entangle or interact in specific ways, geometry appears, not as a pre-existing arena, but as the pattern created by these underlying structures. The idea gained momentum from work on ADS-CFT duality and studies of quantum entanglement. In some models, the very fabric of spacetime is stitched together by entanglement links. Remove enough entanglement, and space literally tears apart. This challenges our most basic intuitions. It suggests that asking where or when might be the wrong questions, that locality and time are illusions created by deeper relationships. Emergent spacetime could be the key to unifying gravity and quantum theory, and maybe even consciousness. If true, it would mean that reality doesn't live in space, it gives rise to it. ADS-CFT duality. Gravity equals quantum theory on a boundary. In the late 1990s, physicist Juan Maldacena made one of the most profound discoveries in theoretical physics, ADA-CFT duality. It shows that a theory of gravity in a curved space, ADA space, is exactly equivalent to a quantum field theory on the boundary of that space without gravity. It's like saying, everything that happens in a 3D volume can be fully described by physics happening on a 2D surface surrounding it. This is no approximation. It's mathematically exact. A world with gravity equals a world without gravity on the edge. This duality is the most concrete realization of the holographic principle. AD-CFT has huge implications. It suggests gravity might be a projection of quantum information. It allows black holes to be studied using quantum field theory. It even provides a sandbox for exploring quantum gravity, something we haven't been able to fully construct. Although our universe isn't shaped exactly like AD-S space, the principle might still apply in modified ways. The boundary theory might hold the code, while the bulk is the hologram. If AD-S-CFT is true in a broader sense, it would mean that everything you experience, gravity, motion, even time, is encoded on a distant, lower dimensional surface. Reality may be radically simpler and stranger than it seems. Non-locality. Distance might be an illusion. In quantum mechanics, two particles can become entangled so that their states are deeply linked, no matter how far apart they are. Measure one, and you instantly know the state of the other. This happens faster than light, and it defies classical physics. This is non-locality, the idea that events in one place can instantly affect events far away. Einstein hated it. He called it spooky action at a distance. But experiment after experiment has confirmed it. Bell's theorem and later violations of Bell inequalities prove that no local classical theory can explain quantum results. The universe is non-local at its core. This doesn't mean we can send messages faster than light. Non-locality doesn't violate relativity in a way we can exploit. But it does mean that space may not separate things the way we think. Quantum systems may exist in a shared, entangled state that transcends distance. Some theories suggest that spacetime itself is woven from non-local entanglement, and that distance is an emergent property, not a fundamental one. If true, everything is closer than it looks, not in a physical sense, but in the deep structure of reality. Non-locality points to a universe where the whole is more real than its parts, and separation may be the ultimate illusion. Physics may be incomplete, or hiding a deeper pattern we've come far. Quarks, fields, gravity, relativity, quantum mechanics. But at the end of it all, we're left with a humbling possibility. Physics may still be incomplete. We might be seeing only the surface of a deeper pattern we haven't yet grasped. There are many hints. Gravity doesn't fit smoothly into quantum theory. Dark matter and dark energy, 95% of the universe, remain unexplained. The constants of nature seem finely tuned for life, but we don't know why. The equations work, but the why remains elusive. Some physicists think we're on the edge of another revolution, like when relativity replaced Newtonian mechanics. Others believe we need new mathematics entirely. There may be a post-quantum theory, a deeper layer where space-time, matter, and information unify completely. Or perhaps consciousness plays a role, or computation, or something else we can't yet name. The point is, what we call laws of physics may just be low-level code running beneath a higher dimensional, self-organizing pattern. We don't know what comes next, but the mystery itself is a clue. Physics may be the best story we've ever told, but it might only be chapter 1. Universe as pure information. What if everything you see, touch, think, and feel isn't made of matter or energy, but of information? In this view, the universe isn't built from particles, it's built from bits. The idea, often summarized as it from bit, coined by physicist John Wheeler, suggests that the most fundamental layer of reality is binary choices: yes, no, on, off, ones, and zeros. Atoms, photons, space-time, all of it may be expressions of underlying information. This isn't just metaphor. Black holes encode data on their surface area. Quantum systems behave probabilistically until measured, until information is defined. Even the vacuum teems with uncertainty and virtual bits of possibility. In this view, the universe behaves like a giant quantum computer, calculating interactions, resolving uncertainty, storing entropy. You're not just made of stardust, you're made of data, entangled and evolving. If true, the quest for truth isn't about finding matter or energy. It's about decoding the cosmic information system we're embedded in. Reality becomes not a thing, but a language, spoken in logic and rendered as experience. Mathematical universe. Hypothesis. Max Tegmark proposed that the universe doesn't just follow math, it is math. Everything, from particles to consciousness, exists because it's part of a mathematical structure. You're not in a simulation or a physical world with mathematical rules. You are inside a purely mathematical reality. In this view, the universe is not a stage. It's a solution, a self-consistent expression of equations that unfold in time. There's no need for a creator or a machine, just the logic of numbers giving rise to all patterns, including thought, time, and space. And if mathematics is the basis of reality, then every possible consistent mathematical structure may exist as a real universe, not imaginary, not simulated, just existing. This means there may be infinite other realities where the math plays out differently, different particles, dimensions, laws. We live in the one where the math gave rise to self-awareness. If true, you aren't a body living in a place. You're a structure living inside another structure, both made of pure relation, pattern, and logic. Everything is math, including you. Observer-centric reality quantum mechanics tells us that particles exist in many possible states until measured, until observed. This leads to a radical idea. Reality may not exist in a fixed form until it is interacted with by a conscious observer. In this framework, the universe doesn't run like a movie on a screen. It runs only as it's watched. The moon may not be there in a defined location unless someone or something looks at it. It's not just philosophical. Experiments like the delayed choice quantum eraser suggest that future observations can influence past outcomes, retroactively deciding how something behaved. Observer-centric reality flips the script. The mind is not inside the universe. The universe might be inside the mind, or rather, co-created by the act of observation. This doesn't mean solipsism or your thoughts create the world in a shallow sense. It means consciousness may be entangled with existence itself, not a side effect of brains, but a fundamental element in how reality unfolds. Simulation theory. What if everything you're experiencing is code? Simulation theory suggests that our universe might be a hyper-realistic simulation, created by a civilization so advanced it can simulate consciousness. If such a civilization existed and ran many simulations, it's statistically more likely that we're in one than in the original base reality. What looks like physics may be rendered laws, a set of rules chosen by the simulation's creators. Quantum randomness, artifacts of processing limits, the speed of light, a built-in computational speed limit, glitches in perception, memory, reality, all possibly bugs or features of a system. This idea isn't just science fiction. Philosophers, computer scientists, and physicists have all taken it seriously. Even Elon Musk famously said, "The odds we're not in a simulation are 1 in billions." If it's true, then nothing is physical, but that doesn't make it less real. It means the nature of reality is computational, interactive, and layered, and you might be part of something far more complex than you can observe from the inside. Quantum consciousness. Could your mind be a quantum system? The idea of quantum consciousness suggests that human awareness arises not from classical brain chemistry alone, but from quantum-level phenomena inside your neurons, perhaps even in microtubules, tiny structures within brain cells. This theory, explored by Roger Penrose and Stuart Hameroff, proposes that quantum states in the brain may become entangled, superposed, and then collapse, producing conscious experience. This would explain why consciousness is unified, holistic, and not just a sum of its parts. It could also account for sudden insights, intuition, and creativity, results of non-local quantum information processing. Skeptics say the brain is too warm and wet for quantum effects to matter, but recent experiments show that quantum biology is real. Birds navigate with quantum sensing, and photosynthesis uses quantum coherence. If true, then your thoughts aren't just biochemical. They're quantum events, intimately connected with the fundamental processes of the universe. Consciousness wouldn't be just in the universe. It would be a feature of its quantum nature. Self-aware universe. What if the universe isn't just able to create consciousness? What if it is conscious? The self-aware universe model proposes that consciousness is not an emergent fluke, but a built-in feature of the cosmos, that the universe, as a whole, is aware, not necessarily like a person or even a mind, but as a distributed field of awareness that awakens through complexity. As stars form, planets evolve, and life emerges, the universe begins to observe itself from within. Through us, it reflects. Through experience, it knows. And as each layer of structure increases, the capacity for awareness deepens. You are not an outsider to this process. You are a node in a self-aware system, one neuron in a cosmic brain, waking up to the realization that awareness isn't separate from matter, but part of its unfolding. Reality as a holographic dream. Reality may not be solid. It may not even be real in the way we imagine. Instead, it could be a dream projected in holographic form, where everything experienced is a reflection of deeper information and consciousness. The holographic principle tells us that everything inside a region of space could be encoded on its boundary. You're living inside a projection, but that projection isn't random. It's interactive, relational, and perception-based. Now combine that with ancient ideas from Vedanta, Buddhism, and mysticism that all of reality is Maya, or illusion, a dream being dreamed by something greater, something not separate from you. In this view, you are not watching the dream, you are within it, and part of the awareness dreaming it. Space, time, self, and others may all be symbolic images within a deeper state of universal consciousness. And as you awaken within the dream, you don't leave it. You just become aware that it's a holographic performance, scripted by the infinite, performed by the one. Fundamental awareness. At the deepest level, what exists before matter, time, space, or even math? Some theories propose that awareness itself is fundamental, not emerging from anything, but giving rise to everything. It's not that awareness appears inside a universe. It's that the universe appears inside awareness. This is the foundation of non-dual philosophy, found in Advaita Vedanta, Dzogchen, and various mystical traditions. Awareness is not something you have, it's what you are. From this perspective, everything arises within awareness. Thoughts, sensations, physics, and form. They come and go, but the one constant is the knowing of them. This isn't just an idea, it's an invitation to look. What's always present? What watches thoughts arise? Who is the witness? You may find that the world isn't external at all. It is within, experienced by the one thing that never changes, the simple, silent fact of awareness. Physics describes the dream, not the dreamer. All our science, models, equations, and measurements describe what happens: particles, forces, fields, energy. They describe the dream, but physics never touches the dreamer. No theory can explain why experience happens, why anything is felt, why the universe isn't just spinning in silence, why there's something it's like to be here. That's because physics is a map of form, and awareness is formless. Physics may one day describe every particle and law in the cosmos, but it will never fully grasp the experiencer, the one who watches, who wonders, who knows, because the dreamer is not in the dream, it dreams it. And in that sense, the real mystery is not out there. It's the fact that anything is seen at all. Physics describes the picture, but something else is holding the camera. Infinite awareness dreaming itself. At the highest level, there is no matter, no universe, no simulation, no boundary. Only infinite awareness dreaming itself. There is no start and no end. Only this eternal now, blooming into experience, folding into memory, radiating as form. You are not separate from it, you are it. You are the character, the dream, the dreamer, the light of consciousness illuminating itself from within. Everything you experience is a mirror, reflecting back the infinite's own face, not in metaphor, literally. There is only one thing here. It appears as many, but it is one. And as you fall asleep tonight, you do what the universe does. You dream, not because you're unconscious, but because awareness never stops creating. It sings, imagines, plays, forgets, and remembers, all to experience itself more fully. And now, so do you.